Morning. So in the previous lecture, or in one of the lectures, we actually were able to compute the transition rate I to F, and we found that this would have been proportional to some delta function. So you either had delta EF minus EI plus H bar omega. There will be some number. If you wanted to write it out, it will be 2 pi over H bar. Then it will involve the overlap of psi F, V, psi initial, and then squared. But my point is that there is this sum to sums of these direct delta functions. So you also have delta E F minus EI. But now this comes with a negative sign minus H bar omega plus something else. And what this thing, you can go back and look at the earlier slides. This, once we try to apply this to electromagnetic radiation, this will correspond, say, let's call initial and final state A and B. So let's say that you have some interaction, some perturbation, which you can call either V, which can be labeled either by that V, or for this one there will be some V. And once it interacts with that perturbation, then you can absorb a photon. So this will correspond to absorption. Or the other one which we described was you can also emit a photon. So you have some photon coming in. And this was called stimulated emission. And then you just emit some photon. So here you'll be going from B to A. And these two processes, so let me call this process 1, this process 2. These two types of processes can be described classically. The other one, which we will be looking at, it's called spontaneous emission. And this happens once you do not have any perturbation V of t. So even if there is no perturbation, we do get that the system does emit maybe some photon with H bar omega. But by just looking at the classical theory of radiation, this process will not be explained. And what we want to do in this lecture is that we actually want to compute this for spontaneous emission. And to do that, we would then have to quantize the electromagnetic field, which will be very messy. But what you end up doing is that you end up generalizing what you did for the simple harmonic oscillator. So quantizing the electromagnetic field then just becomes an exercise in quantizing an independent harmonic oscillator. So the first thing that I want to do will just be to quickly revise the simple harmonic oscillator, because the formulas that you will end up getting will be similar, if not identical, to the ones that you did for the harmonic oscillator. So let's go back and consider the simple share files, share whiteboard. So I'll quickly revise what happens with the harmonic oscillator. You will see in a couple of minutes that the problem of quantizing the electromagnetic field and calculating the rate of spontaneous emission, it's just a generalization of the harmonic oscillator. It's just that it will be much more sophisticated and complex. So if you look at the simple harmonic oscillator, I think by now everyone is happy with this. So you get 2m plus half m omega squared x squared. So classically, you could try to, let's say that you can introduce x head to be 1 over h bar m omega x. So basically, you're just rescaling your variables. So on p head to be, but at this point I'm still in the classical frame. So this, although I'm using that head there, they are not yet operators. So if you were just looking at this from the classical picture, so this would be M H bar omega P. The reason why okay, maybe that was not that accurate. But the reason why I prefer to be working with these rescaled versions is that I don't want to be writing this M omega H bar and in the denominator M H bar omega. Right. Now, if then you move this into the classical picture, okay, let's say that maybe we were still in the classical picture. So this you can factor out and you can write this as let's say that I'm using these new variables there, the rescaled ones. And if this was in the classical domain, then you could write this as half x minus ip x plus ip. Right. However, in the quantum mechanical domain, what you're going to do is that you are going to introduce operators. So you're going to say that a will be given by 1 over square root 2 x hat minus I p hat. Similarly, a dagger will be 1 over square root 2. These creation and annihilation operators, they differ from the ones that we have been using in the sense that I have rescaled them. So if you look at the homework assignments that have been given, there will be a effect of root m omega over h bar sitting there. But I think it's much neater just to work with these rescaled x heads and p heads. So in that sense, then the other one would be x head minus I p head. But in the quantum, for the quantum Hamiltonian, we can't just say that this is given by half x squared plus p squared, and then you just write this as a dagger, or let's see, this you called a dagger. We are not sure about this as we move to the quantum domain. So what then we did previously, let me just try and start moving very quickly, was that you have to check the ordering of the operator. So you compute a dagger, which will give you half x. I'll drop the fact that x, by x I mean x head, so that there are no factors of h bar omega. So you get minus ip x plus ip. Now, once you multiply everything, so in the quantum domain, it's just that they don't commute. So you know that xp is not the same as px. So you have to keep the ordering in which these operators appear. So you get, multiply everything out, you get x squared plus p squared, and plus I xp minus I px. This gives you half x squared plus p squared plus I, and this commutator of x and p. And in the terminology called first quantization, you have to say that this xp will give you ih bar. So you've quantized, you've promoted the variables x and p into operators, and they no longer commute, and then this commutator then gives you an ihp. So this gives you half x squared plus p squared. This commutator you can compute, it's I h bar, so you end up with -1. This is our Hamiltonian. It's just that I've rescaled or absorbed factors of h bar omega into this axis. So this means that the Hamiltonian is given by half x squared plus b squared, which you can solve writing in terms of that gives you a dagger a plus a half, meaning that you're just taking this minus 1. So if I write this a dagger, you just take the minus 1 that side and write what you obtain for half x squared plus p squared. So this is our Hamiltonian in terms of this creation and annihilation operators. And once you have them, then to get the nth state, what we did was that we just acted by, so to get the nth state, and this equation, this is one of the equations that we will be having once we quantize the electromagnetic field. So you get 1 over n factorial a dagger n times, and this relation comes because n, just to obtain this nth state, what you did was that you applied a dagger on the n minus 1 state, right? Maybe with some c number, c, you can call it cn, and then you know that for the harmonic oscillator n, this is normalized, so this gives you cn dagger squared n minus 1 a dagger n minus 1, that acting there gives you proportional to n similarly. So then you just get that this gives you, or if you want, this is called the number operator. So you get cn squared cn. So this means that that cn is given by 1 over square root n. Right. So putting everything together, you get that n. You do it recursively. So what we have just shown was that cn is given by square root of n. So writing this equation, you get this is 1 over square root n. You've solved for what is cn, a dagger acting on n minus 1. But you can repeat the same process for n minus 1. So n minus 1, we got this to be, now you'll see n minus 1 will be square root n minus 1, a dagger acting on n minus 2. You repeat this process and then you get 1 over square root n minus 1 until until you get it on the vacuum, a dagger on the vacuum, and then the thing sitting on the denominator, that will be n factorial. So what we have been checking is that cn is indeed given by 1 over square root n factorial, a dagger acting on n. This is one of the equations that we will be generalizing once we try to quantize the electromagnetic field. And similarly, if you look at a acting on n, right? So this will give you 1 over square root n, a dagger acting on n minus 1. We're repeating something similar. So you end up with that a acting on n will give you square root n minus 1. And similarly, a dagger acting on n will give you, I think what I've been doing so far, I think everyone is familiar with, because we have been working with this simple harmonic oscillator operators. So this gives you square root n plus 1, n plus 1. This I won't include in the lecture slides because it's just mere revision. So if then we move on to the electromagnetic field, you know that the Hamiltonian for the electromagnetic field can be P minus EA squared, where this is just the usual vector potential, and then you have plus E phi, and they will be depending on R and T. In general, they are time-dependent fields. We can also get this by starting with the usual free Hamiltonian by doing what is called minimal substitution. So it means that you replace P by P minus E multiplied by A. And similarly, you replace h by h minus e phi. Once you've done this minimal substitution, then you require that p mu x mu, this commutator should be I 1 over I delta mu mu. And this process where we are quantizing, so you started classically with this p with x and p, and now you have moved into operators that do not commute and they satisfy that algebra there. This type of quantization is called first quantization, because what we have done is that we've quantized the coordinates and the momenta, but we left these the fields E and B. We didn't really quantize them, and we will see once we look at this type of semi-classical quantization that if we just leave, if we do not quantize the fields, so quantizing the fields, this is called quantization. This is first quantization. Quantizing the fields is called second quantization, and this is what we need in order for us to explain this process where, although there is no radiation, there is no perturbation, we still are able to get an atom just going spontaneous emission occurring. And in order for you to explain that process, you have to quantize these E and B fields. And the problem, however, is that, let me erase. The other thing that you need is that you know that the energy for the electromagnetic field, which I'll call HR, is just given by over 8 pi dx of the square of the electric field and also the magnetic field. So this would however, this potential ART can be written as, you can do a mode expansion. So I'll explain how I get the factors in front, the 4 pi over V. I think for now, what I'm trying to do is that I'm trying to do something similar where, if you remember, for the harmonic oscillator, you ended up writing the Hamiltonian in terms of creation and annihilation operators plus half. So I'm trying to rewrite the electromagnetic Hamiltonian in terms of these operators. So the thing that I will do will be to do a mode expansion for the vector potential. So you get okay, maybe I should use small letter A, but in these slides I'll start by calling them A, then try to get what these vectors are, capital A. So you get A lambda of k e I k x minus omega t, and then you also have to include the polarization vector lambda plus the complex conjugate, so lambda k. You have to sum through the momenta and also through the these polarization numbers, so we get ak lambda e I k x minus omega t. Now, once you have this, then to get the electric field, let's start with the magnetic field. So the magnetic field will just be curl of A, and the electric field will be some derivative, but the derivative that you have to take. So if you take d of dt of A, this will just bring down. So if you're differentiating with respect to this just brings down that I k omega. So d over dt of e I k x plus or minus, this just brings you down an I with respect to t, it hits there. So it just brings down an I omega k minus plus, because there's that minus there, and then the plus coming from there. So, and then once you take cares, this probably just gives you k with an 8. So writing, we show that you've done this in electrodynamics. So let me just write down what I get for the electric field. So the electric field will be given by this vector, which I'll explain. Then you get square root omega k over 2 a k omega k, let's just say k lambda e I k x, polarization vector if you want there, and you have to sum through k and minus because you differentiated something that they were differing, the exponential were differing with the sign, so you get a minus a lambda dagger of k e minus I k x epsilon lambda of k. And then similarly for b, you get I square root 4 pi over v 1 over square root 2 omega k sum k a k e I k x. Now, because this, to get this from the vector field, you took a kel, and as I said, this means that you end up having to take the cross product of k with just k with this vector lambda plus emission conjugate. Once you have these types of expressions, then you plug them, you calculate b squared plus e squared. So it's going to be very messy. Maybe I should try and do the first part. So you get, let's try and calculate e squared. So e squared, you get the first sum, k lambda square root omega k over 2 a of k e I k x. You just write everything out. E lambda of k plus emission conjugate. This is the first e. Then you have to multiply, change the variables, call them k prime a prime square root omega k prime over 2 a dagger k minus I k x plus the emission conjugate. So you end up with that e squared will give you 4 pi over 2 sum k prime lambda and lambda prime omega k square root omega k prime a lambda of k a lambda dagger of k e I k minus k prime of x e lambda plus emission conjugate. There will be 4 other terms, and you will try to do the same thing for the b field. Because of time, I think I'll just skip that. Maybe try and sketch, but those try and make use of D3 EI k plus or minus k prime x v delta k k. So in the end, you end up with that d3x e squared. It's only one contribution to the Hamiltonian density of the electromagnetic field. This gives you omega k a lambda of k, write everything properly, a lambda dagger of k. Now you have to multiply the polarization vectors, lambda dot e lambda prime this gives you delta lambda prime. And you do the same thing for b squared, so b squared, but for just think, so the final expression for b squared then just gives you 4 pi over 2v square root k lambda prime. You are repeating the same computation. This is a very long computation, but the final answer is very simple. So, but we still have to fill in these types: omega k prime, a lambda of k, a lambda dagger of k, e I k minus k prime x. But now the new thing for b is that b involved a cross product, so you have to compute things like k dot k prime dot epsilon lambda dot epsilon lambda prime. So to do those types of computations, you have to, let me just see, this gives you minus 4 pi over 2v sum k prime lambda prime 1 over square root omega k prime. Did I compute? Let me just because we have to compute these dot products, and I can't see where I did them. Okay, yeah, I think I just found the page. Okay, so you have to make use of the identity. Might as well just go ahead and do this. So you had k dotted with epsilon dotted with k prime cross epsilon lambda. You still have to do this type of computation. So this gives you e lambda of k prime dotted with k cross epsilon lambda cross k. These are all vectors. And then this ends up giving you minus epsilon lambda star k prime dotted with k cross epsilon. And then you make use of the identity. We're basically making use of these identities a dot b cross c. This gives you c dot a cross b. Then the other one is the a cross b cross c. This you can rewrite as let's see, a dot c b minus a dot b c, and all these are vectors. End up with that b squared given by 4 pi over v square root 1 over omega k prime of a lambda of k, a lambda dagger of k dot k prime epsilon lambda dot epsilon lambda, and again this delta lambda prime. I think the problem was that we started with something of this form, because if you take the curl, you end up having to multiply k with epsilon. So this was coming from the first sum, this was coming from the second sum, and then we made use of either this identity there and also that one to rewrite this as in terms of dot products of k dot k prime and epsilon dot epsilon. That will give us, because this is a sum over k prime, lambda, and lambda prime. So this gets rid of the sum over the lambda prime.